Hey everyone, thank you all so much for coming. My name is Gautam. I'm a software engineering lead at Neuralink, and today we're going to be talking about Neuralake, which is our internal data platform. And the recurring theme through this presentation is going to be that we are building really simple systems for really complex data. And simple doesn't mean easy, and I really want to show what we've built over the past couple of years. So to start out, I can introduce myself. So I'm Gautam. I'm a software engineering lead at Neuralink for our full stack internal development team and our data engineering team. So our team does a whole bunch of stuff. It's all really interesting. It's a really fun team to work on. Lots of unique verticals to drive. We do data engineering, some of which I'll talk about today. We also do manufacturing, software. We do full stack development for lab management tools. We build visualizers for billion-pixel images. We have a lot of different things going on. And yeah, I can't even cover a tiny percentage of it today. So if you have more questions, please feel free to come and ask me afterwards. So before we talk about Neuralake, let's talk about Neuralink. So I'm sure some of you have heard about Neuralink in the news, but for those who haven't, so Neuralink is a company creating a generalized brain interface. And what we mean by that is a generalized I/O interface into the human brain that can read and write signals from the brain. And the reason we're doing this is to restore autonomy and help those with unmet medical needs. There are millions of people in the world that suffer from not having their medical needs met. People with spinal cord injury, people with blindness, people with ALS, and more. And what we want to do is solve these ailments of the brain and of the body with a generalized brain interface. And in the long term, we really want to unlock human potential for what it means to be a human and really unlock what the human species are capable of. So how are we doing this? Well, we have a stack, and the Neuralink stack is composed of three main components. So on the left here, you can see that we have our device. It's called the Link. And this is an invisible device that is surgically implanted into the cortex of the brain. You can see that there is a chip. It's a circular disc about the size of a US quarter. And that chip has long, thin electrodes coming from it. Those threads are extremely thin, much smaller than a human hair, extremely flexible, and can be inserted into the brain with minimal invasiveness. And these threads have electrodes on them that can sense brain activity. So as neurons activate, we have signals going up these threads into the chip. And the threads are inserted via a surgical robot. These threads are too thin and too flexible to be inserted by a human hand. So we've built our own neurosurgical robot to insert these threads, avoid vasculature, and move with micron precision. And once these threads are inserted and reading brain data, we send signals over Bluetooth over to neural signal decoding software. And this software can classify brain signals into something useful in the external world. This might be moving a cursor on a screen. This might be moving a robotic arm. There are many things you can do once you have these signals on a computer, and the purpose is to decode neural intent. And again, the purpose of this is to restore autonomy. So we want to help people with unmet medical needs. And two cases here that we have are telepathic control of a computer cursor, as you can see on the left, for people who have motor impairments and are unable to move their arms in a way to control a computer. We want to allow for telepathic control. And this year, we did start our first clinical trial, and we have one person who is actually benefiting from this therapeutic case. And another example of unmet medical needs that we are hoping to address is the ability to cure blindness. You can imagine if you have a perfectly working visual cortex, but have other issues with your retina or optic nerve that prevents you from being able to see, we can send signals directly to the visual cortex and stimulate the brain and induce vision. So both telepathic control and restoring vision are two applications of this device. And you can imagine, because our brains make up a core part of who we are and what we do, there are many, many, many applications for helping people around the world. So let's talk about data at Neuralink. And you can imagine there's a lot of data involved here, right? We have data from the brain, we have data from our devices, and we have a lot of data to manage. And the data is incredibly complex. So Neuralink, the Neuralink stack I just described, is one of the most complex medical devices to have ever existed. And we have correspondingly complex data. We have, of course, the brain signals and the signals that come from the device. We have telemetry coming from the device that's safety critical, that's indicating whether the device is functioning properly. We also have the brain signals themselves. And we also have manufacturing data. As we manufacture our devices, we have information about the manufacturing history and machines on the manufacturing lines. We have histopathology data that is large billion pixel images of tissue that we use to assess the safety profile of our devices. We have data collected during surgeries to make sure that our surgeries are safe and effective, and more. This data is incredibly multimodal, it's incredibly complex. We have images, we have video, we have huge images, we have logs that end up being terabytes large. So this data is very, very, very complex. It's not just simple tables or simple log stores. There's a lot of different modalities we need to address here. And we have a really strong design philosophy for our data systems. We want to have simple systems. And again, simple doesn't mean easy, but simple means that we want systems that can scale down to a single developer machine and up to stateless clusters. The development experience for a developer who is building the system should be seamless. Running something on your local laptop should be the same as running something in production. And we want to really prioritize the local development experience. Instead of having large distributed services that we need to put up, like a Spark cluster, to be able to access our data, which runs in a JVM and can run slow on a local laptop, we want to make sure that we prioritize the local development experience by using composable libraries. And we want to avoid large stateful distributed clusters for our data lakes and warehouses. We don't want to have a database cluster that we need to maintain in order to store and access our data. And finally, we want to have code that's a catalog in and of itself. And what we mean by that is we want to be able to generate a catalog that contains all of our data sources so internal users can access this data and discover it. And we don't want to have a database server and like all this complexity to maintain when we have this catalog application. We want to just be able to define a table in code and have that generate a catalog. So you can see the simplicity here from the end user experience. Internally, when users access our systems or when developers build these systems, they can replicate a production environment locally. They can build a system easily using composable libraries, and end users can access data without us having to maintain a bunch of different services. So there's three main prongs that I'm going to cover here today. We're going to cover ingestion, discovery, and access. So ingestion is the ability to ingest data into our systems. So we want to have low latency streaming ingestion pipelines. And we want to have an elegant way to handle schema versioning and backfilling of our data lakes. And as many of you can guess, we're going to talk about Delta Lake a little bit as a part of this. We also want to allow for discovery. Now, with all of this complex data, it's really hard for people to know where all the data lives. No one person knows where all the data lives in their heads, right? They need to be able to organically have a certain query or certain problem they're trying to solve, and then look at our catalog and find data organically. So we want a simple data catalog that's generated from source. And we want low-code dashboards that people without software experience can build that are generated from our catalog definitions. Again, a single source of truth for all of our dashboarding, data cataloging, and so on. And then it should be easy to access. Now, a software engineer can, of course, write a query to a Delta table and get some information, but we want everybody at the company to be able to access our data. So our goal is to have a single click to get a data frame. You click a button, copy some code, and you have a data frame on your computer that you can play with and query. We also want to create auto-generated SQL and REST APIs from our data catalog so that our internal dashboards can query these APIs. And again, using the single source of truth of the data catalog. So this is a 32,000-foot view of what our Neuralake data platform looks like. And this is really just a part of it. Again, I can't cover all of the complexity of our data today. But we have data sources. We have offline batch writers and low latency writers for processing that data and putting it into our data stores. And we have our data stores themselves. We have Delta Lake, we have relational stores, and so on. And something you'll see from this talk is that our data stores can be spread across multiple different instances. So we can have data in Google Sheets if we have data in spreadsheets. We can have data in Delta Lake. We can have data in Postgres tables if we have high transactional needs, which we do. And all of this data is then easily discoverable and accessible via a data catalog, via a Python client, and via visualization tools. And what you'll see is that the catalog, the Python client, and the visualization tools all come from the same source. There's a single source of truth for defining these, and then everything else is auto-generated, which makes maintaining these systems very easy. So first, I'm going to focus on the data sources, the low latency writers, and how that data ends up in our Delta Lake stores. And there's a lot more to talk about with offline batch writers and so on. So if you're interested in those use cases, find me afterwards. So before we talk about our data ingestion, let me just give you some primer on our technologies we use. So we have Delta Lake, and we use the library Delta RS in our real-time ingestion pipelines. So what is Delta Lake? I'm sure a lot of people here are familiar, but for those who aren't, Delta Lake is an open source project, and is essentially a file protocol or file format that allows you to have ACID-compliant transactions on top of blob stores. A lot of data lakes before Delta Lake were just Parquet files on S3 or on a different blob store. And the downside to that is you can't really get any kind of ACID compliance across multiple files, right? You can't have transactionality across multiple files because these systems only allow for atomicity for a single file, and you might have partial writes if clients are reading from multi-file stores while you are also updating multiple files at once. And we don't want that. So with Delta Lake, we have a transaction log and Parquet files on S3, and as long as the client and the writer both follow the protocol, which means that they both read from the transaction log before pulling the Parquet files, we can ensure that all of the Delta writes are shown in a transactional way. So you'll never have partial writes seen by the client. And the Delta Lake protocol is implemented by Delta RS. So Delta RS is a Rust library that implements the Delta Lake protocol. It allows for writing and reading of Delta table stores. So the Delta RS library takes care of both reading and writing to Delta Lake, updating the transaction log, doing atomic commits across multiple files, and so on. The Delta RS library is written in Rust. It's incredibly performant, and it's highly concurrent, and it also has Python bindings. So you can import the Delta Lake library in Python, and you can run it locally on your machine. You can run it in a stateless cluster, and the developer experience is the same. So we're going to talk about a use case for Delta Lake. We have multiple Delta tables. Each of them have slightly different use cases at the company. We're not going to cover all of them, but I do want to cover one interesting use case that we have. So this is real-time or close to real-time data ingestion into our Delta tables. So on the left, you can see that we have the N1 implant being used. And while it's being used, we have data being emitted. We have events being emitted from the device. These may contain neural signals. And we also have events being emitted from the usage of a computer. So the individual using the Neuralink device is going to be playing a game on their computer. They're going to be moving a cursor in some way. And information about that cursor and about their neural signals will be being sent into an ingestion API. And this ingestion API stages these events onto a message queue, which are then consumed by a writer in batches written to Delta Lake stores. And downstream, those are consumed by Rust-based query engines. And the purpose of this is to train a model to better calibrate to the neural signals by a user. So as we have neural signals leaving the device, we also have events on the game itself from the cursor movement, and we want to align the timestamps of these and create labeled data that can be trained on. So this whole pipeline uses Delta Lake as the main store for the labeled data, which is then queried via Delta RS or other Rust-based query engines. And that data can then be trained upon. And this whole pipeline makes it so that the labeled data is available in seconds. So in a few seconds, we have all of the data available for training, and this is updated live. And the reason we want such real-time availability is because during a session, our engineers might train multiple models. And we want to be respectful of somebody's time if we're engaging in a session with them, and we want to make sure that we can train a model as quickly as possible to try to converge on an optimal solution. So let's really focus on the message queue, the writer, and the Delta Lake instance. So we're going to talk about how the writer actually writes through the Delta Lake instance while consuming from the message queue, and how the end-to-end flow works for data to arrive in the Delta Lake store. So the Neuralake writer instance has 3 primary processes. We have a writer process, a compaction process, and a vacuum process. Now, these 3 processes each have a different function. The writer process, as you might guess, consumes batches of messages from the message queue and writes them in batch to the Delta Lake table. Now, there's a problem here. We have messages arriving very rapidly in real time. And if we write a new write to Delta Lake for every batch of, let's say, like 10 messages, then we'll end up with a lot of small files in our Delta table. And if we have a lot of small files in our Delta table, then we have a problem, because downstream readers need to read a bunch of small files on S3. And that means that we have high latency for our reads, because we need to do individual GET requests for multiple files. So instead of doing that, we have a compaction process that once files are written to S3 at some cadence, right now we have it configured to be once a minute, but this can be tuned. We have a compaction process that reads all of the files within a partition and compacts them into a single file. Now, in Delta Lake, this is possible because, again, we have ACID compliance across multiple files. This wouldn't be possible if we had a bunch of just Parquet files on S3, right? So in this case, we read all of the files that are in the Delta table, compact them, and write back a single file. And now when clients read that single file, it's very fast to be able to get that single file into memory. Now there's a problem though. So with a compaction process running alongside a writer process, we need to make sure that all of the commits themselves are serialized. Now remember, Delta Lake has a commit file, and it has Parquet files. And both readers and writers access the commit file, the transaction log, before they access the Parquet files. Now, if 2 simultaneous processes are trying to write to the same file, you could have a conflict, and this could lead to data loss, right? So we need to make sure that we have a serialized commit, even if our writes are happening simultaneously. So the compaction process takes a long time. It takes some time for compaction to run, but that can run in parallel while writes are continuing to come in. And once the compaction is complete and the compacted file is written to S3, we can then serialize a commit and commit to our transaction log. And we do that by, there's a custom put if absent semantic in the Delta RS library where we use DynamoDB, and we take a lock on the commit file itself. And once we take a lock on that commit file, we can then commit and then release the lock, and then the other process can write. And there's some more complexity here because when a process has a lock for a critical section, it takes a time to live for that lock, and while holding the lock, a writer can crash, right? Or it can pause indefinitely for any reason. You could have other processes on the machine, you could be thrashed by the scheduler on the OS, and so on. So when this happens, we need to have a custom put if absent semantic with a repair mechanism on the DynamoDB lock itself to make sure that if a process crashes or pauses while holding the lock, we don't have data corruption. I have a link in here for another talk that describes the put if absent semantic in detail, so I recommend you all take a look at that. And if you have questions on this, please find me after. So that's how data gets into our system. We have writers, we have low latency, we have high latency batch writers, and both of these kinds of writers are writing to our Delta stores. And all of this data is available, so let's talk about data discovery and data access. So, like I said, we have a data catalog, we have a Neuralake Python client, and we have visualization tools. So all of this allows internal users to be able to access our data without needing to ask a bunch of people where data is stored or know all of the different Delta tables, all of the different Parquet files that lie on our blob store, and so on. We want to make data access really easy internally at the company. So I'm going to start off by talking about the Neuralake Python client. So the Neuralake Python client has a very simple structure. We have a catalog, which can have many databases, each of which can have many tables. So this is a very standard data catalog structure. And a table is really just a way to get a data frame via the Neuralake Python client. So it's just an abstraction to be able to get a data frame. And when we use the Python client, it looks something like this. We have a very clean API. We have the ability to get a data frame for a specific database, for a specific table. In this case, this table is called normalized band power. You can pass in some filters, and you can collect the data frame. And the return data frame is actually a subclass of the Polar's lazy frame. So Polar's is another Rust-based data frame library. And Polar's is very similar to Pandas, but much, much more performant. Because it's written in Rust, it allows for very, very powerful concurrency, and it is able to process data very quickly. And the lazy frame allows us to lazily execute these data processing queries. So queries are only run once collect is called and evaluated lazily. And we've subclassed that, so every table returns a Polar's lazy frame that can then be executed on. And something we have planned is to actually do push-down queries where we actually filter on the Parquet files themselves before even pulling them over the network, so we can lazily evaluate and optimize even our network calls. So how do you add tables? So you saw that table, it was normalized band power right here, right? So how does somebody add that? Well, it's super easy. So all a developer has to do, once they've set up their data ingestion pipelines, once they have data being written, is they just have to write a single line of code. We have declarative syntax that looks like this, where they can declare a Parquet table or declare a Delta table. We support both. And they can essentially just give a name, the URI, the partitioning scheme, and some documentation information for the documentation that's automatically generated. So this is a single line of code. It can take a developer maybe a few minutes to write, and their table will be available in the catalog. We also have custom functions that can be a part of our catalog. So you might imagine a view that involves consuming from multiple Delta tables or multiple Parquet tables. You might have a function that queries a Google Sheet or a relational database and gets some data back. We want to make that data also available for our internal users. So in this case, we have a function. It's called robot insertions. The doc string is automatically pulled into our documentation. And all they have to do is add the @table annotation at the top. And once they add the annotation, that is automatically registered as a table in our catalog and available inside of our catalog. It really could not be easier. And the catalog looks like this. So you can see we have an auto-generated catalog. We have all of our databases, all of our tables, and internal users can just go onto our internal site. They can access this catalog. This catalog does not hit a database to get its information. This catalog is a static site that's generated in our CI and deployed, and does not have any kind of backing to it. It's auto-generated from the code that you saw earlier. And in the catalog, we have the view of a single table. And you can see here that we auto-generate the code for the Python client as well. So an internal user can literally go to the catalog, browse a few tables looking for the data they want. Once they find the table, they can just hit that copy button. They can go to Jupyter Hub, which we host internally, and they can just paste that code into a Jupyter notebook. And once it's in the Jupyter notebook, the code automatically can be executed, and the Jupyter Hub instance is already authenticated to S3. It's already authenticated to the buckets it needs to access. So an internal user doesn't need to wrangle with credentials or logins. They don't need to worry about where the data is stored. Just copy, paste, analyze data. So in addition to our catalog, we have read-only APIs that are also generated from our table definitions. So when developers define a table in Python, we create read-only APIs, and these read-only APIs accept HTTP SQL queries. They also accept the Postgres wire protocol. And this means that dashboarding tools like Grafana can be configured to point to our read-only APIs. So just to really emphasize the simplicity here, all a developer has to do is add a single function like this, or a single line of code, a single command like this, declaratively. And that is already available in the catalog automatically, and it's also available in the dashboard. The developer doesn't have to do anything else. And internal users can then set up their own dashboards for this data source. So I want to deep dive into how exactly this works. And at the center, you can see that the Python client really is the center of all of this. The Python client, which contains the table definitions, generates everything you see here, and no additional action is needed from the developer. Again, from a developer experience, this is simple. I just add a function. I don't need to worry about anything else. So the Python client itself uses polars and Apache Arrow in order to query the Delta tables and the Parquet files. So with a single declarative command, a developer can create a table definition, and we've already written the code to automatically configure that to be a Apache Arrow query that fetches from S3 or from whatever data source you have in mind. And the result is a polars lazy frame that we have that lazily evaluates the query once the user actually wants to do something useful with it. And once that table is defined in the catalog, then we generate the catalog website. And all we do is we take the table definition that you saw, where we have the annotated function, or we have the declarative syntax for that table, and we just serialize that to JSON in CI. So once you merge your code to the main branch, we serialize the result to JSON, and then we generate the static site, we deploy the static site. It's easy. No database to manage for the catalog, nothing. The site is up, and the catalog is super responsive, and doesn't require any additional maintenance. And users can use the Python client directly. So internally, if somebody wants to just pip install Neuralake, they can do that on their own local machines. They can use Jupyter Hub. Jupyter Hub comes preloaded with a Neuralake library. They don't need to install it on their notebook. It's just, everything is just ready. One click to copy, one click to paste, one click to run. Very easy. And in CI, we also auto-generate a row API config. So some of you might have heard about row API, but for those who don't know, row API stands for read-only API and uses Apache Datafusion, which is a query library that executes logical plans on data and is written in Rust. And what we do here is we generate a row API instance. And row API accepts HTTP requests containing SQL. It accepts GraphQL queries, and it also accepts the Postgres wire protocol. So you can literally configure a pSQL client, connect it to our Neuralake stores, which is auto-generated from a single line a developer wrote to add a table, and you can pretend like you're interacting with a Postgres database. So that is incredibly powerful, and row API is stateless. You can scale it up, scale it down just by adding more instances, and row API allows for really fast querying. And then Grafana, the dashboarding tool, can simply plug into row API, because row API takes HTTP requests containing SQL. It can be configured as a Grafana data source, and the Grafana dashboard can then just be built by users. So if I'm a developer and I just created, for example, a new way to ingest manufacturing data from our manufacturing machines on our line, and all of this data is being streamed into my Delta Lake table, all I have to do is add a single line, and I can tell the manufacturing team, hey, you guys get dashboards, you guys get Jupyter notebooks, you guys get an HTTP API you can access the data from, and it's all really easy. People who aren't software engineers but know a little bit of Python, know a little bit of scripting, can use the Python client. They can use Jupyter Hub. People who don't know any Python at all can use Grafana and configure their own dashboards. And this just makes it really powerful for us to access all of our data internally. So this allows us to build the best product we can, because our data is so complex that we really need to be able to make data access at the company incredibly easy. Otherwise, we would not be able to make good decisions. and we would not be able to help millions of people. So in conclusion, the way we do this is we define tables in code. Everything is defined in code, one time, one command, one function, and we can generate a catalog, API, and dashboarding tools, and we don't need to maintain a catalog database at all. And read and writes both scale down to a laptop, so you can run the Neuralake client on your laptop. You can, if you're developing a writer, you can run that on your laptop too. The Neuralake writers that write data to Delta Lake can run as a single process on your laptop. Very easy. There's no overhead of a JVM. There's no overhead of trying to run Spark locally. And this means that we can also scale it up to a stateless cluster. And these clusters scale, right? Because they're stateless. You can just add more instances. And this flexible design makes it really easy to extend all of our systems. So you can add offline batch processing. You're not limited to just Delta Lake and real-time event ingestion. You can have offline batch processes running in Airflow, which we do. You can have any kind of backend for your data. You can have a Google Sheet and just have the Neuralake Python client read from that Google Sheet if that's useful to you. You can read relational data. We have relational databases. We have highly transactional workloads that we need to have in relational databases. We don't want to exclude those from our data lake. And all you have to do is just add another line to your Python client. Very easy. And the Rust-based systems that I talked about, so Polars, Apache Datafusion, Delta RS, really allow for high performance data access. Writing code in Rust means that you can write code with high concurrency without worrying about race conditions because of the inherent safety of the language. And it means that we can build systems that are composable libraries that can just be imported into a developer machine and then run in production and scale up and down without needing to worry about the overhead of larger systems. And the real champion here is Delta Lake, which allows for us to do all of this because it allows us to have ACID transactionality on blob stores. We can have commits across multiple files on our blob stores. And we don't need to maintain a database server. We don't need to maintain a big cluster that stores our database that we need to maintain. So I do want to thank the Neuralake team. So we have some of the most brilliant people that I've ever worked with in my career on this team. And they've contributed immensely to this effort. And I feel incredibly privileged to be able to work with people like this every single day. I think we've built a really unique culture at our company where we have a really high bar for talent. We have really talented individuals who are incredibly mission-driven and determined to help millions of people around the world, and who are interested in building simple systems to really manage our data. And again, simple isn't easy, and everybody here has worked incredibly hard to build these systems. And finally, before we go to Q&A, I want to leave you all with some quotes. These are from participants in our clinical trials. We have started clinical trials in the United States as of this year. And there are people that benefit from these devices whose lives have been changed by the use of our device. And this is honestly what keeps me going. This is what keeps most people at our company going, is knowing that we can help people in this way, and knowing that we can change people's lives and plan to change many, many more people's lives. Okay, one more quote. And to be honest, I get a little emotional even thinking about it, because it really is a privilege for us to be able to work on such amazing engineering work and work on bleeding edge technologies and also help people in the most fundamental and meaningful of ways possible. And to really have that be the way I spend most of my waking hours is an incredible privilege. And I personally feel incredibly lucky, and most of my colleagues also feel incredibly lucky with the way to spend their time. So if that kind of an engineering culture interests you, if you want to help billions of people around the world, if you want to work on these kinds of bleeding edge data systems, we are hiring. So I encourage you all to go to neuralink.com/careers, and I will be available after this talk, so please come and find me as well.
And I think we're out of time. Thanks everyone for all your questions.
Great, thank you all so much.